Hello. Today is the tutorial class. We have been trying to see several problems in bending moment and shear force diagram of beams. Let's see some more example in this class. You see, now let's start with this problem. This is if you see, this is a beam where your support A is fixed support, and then we have a roller at C, and then in addition to that you have an internal hinge at B, right? And then the beam D is subjected to uniformly distributed load of kilonewton per meter. Okay, this is kilonewton per meter. Okay. Now you see, if you remember what we discussed during static equilibrium conditions and indeterminate structure, if you do not have this internal hinge, then the structure is statically indeterminate structure, because this is fixed support where your number of reaction components are 3, and then an additional reaction component at the roller support, which is 1. So total reactions are 2. Total reactions are 3 plus 1 4, and then number of equations you have is 3. Okay, so this is a statically indeterminate structure. But now if you put one hinge here, then this hinge will give you one more condition, and the condition is the moment at this location, at the hinge location, is 0. And that condition will give you one more equation, and that equation can be used along with other equilibrium equation to solve for the unknown. Now we will just going to demonstrate that here. Okay. Now first what we do is we divide the entire beam into two parts. One is AB, this side of the hinge, and then BD, the other side of the hinge. Okay. Now let's draw the free body diagram of this part, AB. Free body diagram of AB will be at this point. This is AY reaction, then AX reaction, and moment, sagging moment positive. This is MA. Okay. This is subjected to uniformly distributed load 10 kilonewton per meter. This distance is 2 meter. Okay. And now since this is at this point, there will be no moment, only it will be Bx, and then we are not considering any axial force, so there will be no Bx, only force will be Vx, the shear force, or let us not write Vx here. Let us denote it as Bx, By, which says that the hinge reaction at B. Okay. Now if I draw the free body diagram of the other part will be this, and this at C there will be vertical component which is Cy, then uniformly distributed load which is 10 kilonewton per meter. This is 2 meter, this is 4 meter, and then since Bx is shown downward here we have to show Bx upward, By upward to satisfy the equilibrium. And let's take Bx and Bx here, which is in this direction, and here you show Bx in this direction. So this is the free body diagram of this is the free body diagram of this part, this is the free body diagram of this part. So hinge reactions are Bx and By, and in this case again Bx and By, but here Bx and By and Bx and By here shown in opposite direction, right? Now next is, once the free body diagram is drawn, next is apply the equilibrium condition. Now from this, if I apply summation of Fx is equal to 0, so this gives me Bx is equal to 0, Bx is equal to 0, right. Then take moment about B, summation of MB is equal to 0, and what are the forces will contribute? Cy and this force, and Cy is anti-clockwise, so Cy into 4 minus Cy because it is anti-clockwise, then plus moment due to 10 kilonewton per meter uniformly distributed load. It is distributed over length 6 meter, and since it is uniformly distributed, line of action of the resultant is at the mid position. So total load will be 10 into 6 meter, and then line of action is 6 by 2. So this is 0, and this gives me Cy is equal to 45 kilonewton. Okay. Okay. Now once we have Cy, now let's use another equilibrium equation, summation of Fy that is equal to 0, that gives us By plus Cy is equal to total load, which is 6 into 10. Cy obtained already 45 kilonewton meter, and we will get By is equal to 15 kilonewton. So this gives you 15 kilonewton. Okay. So support reactions here and hinge reactions are determined. Let us now, you come to this free body diagram. Bx is already determined here, By is already determined here. Only thing we need to determine is Ax and Ay. Now here one point to be noted, you see, if you start here, we started from this free body diagram. Okay. Now instead of that, if you start from this free body diagram, what happens? Your number of unknown you had is if you do not have calculated the support reactions from this free body diagram. If you start your problem or solving the problem with this free body diagram, your number of unknowns are Ax, Ay, Bx and By. So 4 unknown, and number of equations you can have at most 3. So you cannot solve it. Therefore, even if you have divided the structure into several parts, which part to take first, that you need to decide based depending on the problem. There is no standard specification which can tell you that. You have to learn that through exercise, through practice. Okay. Only thing is, you need to keep in mind that your number of unknown should not be more than the number of equations in any free body diagram. Now, so Bx and By are already obtained. Only thing we need to obtain is Ay. Bx is equal to 0 here. So again, summation of Fx gives me is equal to summation of Fx is equal to 0, gives us Ax is equal to 0. Okay, and then if you take summation of Fy is equal to 0, this gives us Ay minus 10 into 2 minus By. Please note here By is in opposite direction. Okay, and By is already 15 we obtained, and then finally Ay will be 35 kilonewton. Okay. Okay. So these are support reactions, Cy, By and Ay. Okay. Next is draw the bending moment and shear force diagram. Okay. Now let's do that. First, what we do is, you take here, first you take a section here. At a distance x from x, and this x varies from A to C. Okay, means x varies from 0 to 6. If we take that, then what would be the free body diagram? The free body diagram will be this is Ay, this is ay. Another thing we have not yet determined, that is moment at A. Moment at A you need to determine by taking moment about A. If you take moment about A, take moment about A, moment about A is equal to 0, and then what, or you can take moment about A is equal to 0, or you can take moment about B is equal to 0, because this is hinge, so there will be no moment, and if you take that, then your, once again let me draw the free body diagram here. This is MA, this is BX, and then BY. Okay. Now this is B. You take moment about B is equal to 0. Now forces will contribute is AY, MA, and this. So AY into 2, which is clockwise, then again MA clockwise, and then minus 10 into 2 into 1, which is anti-clockwise, that equal to 0. AY we already obtained 35. So if you substitute that, you will get MA is equal to MA is equal to 50 kilonewton meter, minus 50 kilonewton meter. Okay. So now all reactions are determined, right? You have AY, CY, BY, and then MA is 50 kilonewton meter. Now let's draw the free body. Let's find out the bending moment and shear force diagram. Take a section here at a distance x from A, and this x varies from A to C, means x varies from 0 to 6 meter. Okay, and the free body diagram will be like this. AY, AX I am not showing because AX is 0. This point is B. We have an internal hinge. This is 10 kilonewton per meter, and this distance is x. At this point shear force is Vx, and bending moment is Mx. Hogging bending moment and shear force, which provides clockwise couple. Okay. Now take summation of Fy is equal to 0, which gives me Ay, which is positive, then minus Vx, then minus 10x is equal to 0. 10 is the intensity of the uniformly distributed load. Ay is already obtained as 35 kilonewton. So from there Vx becomes 35 minus 10x. Okay. So this is how Vx, the shear force, varies from point A to C. Okay. Now let's see bending moment. You take moment at this point, summation of Mx is equal to 0, moment at a distance x, and this gives you moment Mx, this is anti-clockwise direction, and then plus Ay into x, Ay produce clockwise direction moment, and then minus 10 into x by 2, that is the load moment due to external load UDL, that is equal to 0, and from there we get Mx plus Ay is equal to 35x minus 5x square is equal to 0. So, this gives mx is equal to 35 x minus 5 x square. 5 x square. You see, this is the distribution of moment between A to C. So, we have taken one section here, that section gives you distribution of and moment. We have calculated shear force and bending moment at this point, and that gives me how the shear force and bending moment varies between A to C. Let us take one more section between C to D. That section is this. Okay. Now, if you remember, if you break a system, now you have several subsystems, right? Now, all the subsystems should satisfy the equilibrium, right? Now, sometimes what happens, if you in the same example, if you see here, we divided when we started, we divided the entire beam into two parts. One is AB and BD. We started our calculation with this part, and then once this is done, we move to this part, because this the number of this was easier. Otherwise, if we start with this, then the number of unknown will be more. So, which part to, as I have already said this before, which part to take, that you need to decide based on the problem. And also sometimes what happens, both parts probably give you the both the subdivision, both the parts may give you the information, but probably one part give you the information, or dealing with one part will be much easier than the other part. For instance, if I take this beam and take a section between C to D. Now, this section divide the entire beam into two parts. One is this and one is this. Let us draw these two parts separately. Now, these two parts will be, the first will be this. This is the entire beam. This is fixed, and then you have internal hinge here, and then roller and uniformly distributed load. Now, we take a section here, and this distance is x. This distance is x. Okay. Now, we have two parts. One is this part and another one is this part. Okay. Let us first draw the free body diagram of this. Free body diagram of this part will be AY and then CY, uniformly distributed load. This is Vx and this is Mx, and this distance is x. This is the free body diagram of this part. This is 10 kilonewton per meter. Okay. Now, if I draw the free body diagram of this part, free body diagram of this part will be this Vx and sagging moment positive, this, and this distance will be, total distance is 8 meter, this distance will be 8 minus x. Okay. And this is 10 kilonewton per meter. You see, if I calculate Vx from this free body diagram, Vx and Mx from this free body diagram, and Vx and Mx from this free body diagram, both will give me the same expression, similar expression. But computation with this free body diagram is easier as compared to this. Why? Because the number of forces, a number of reactions are less here. Now, if I take this, then summation of Fy is equal to 0. This gives me Vx minus 10 into 8 minus x is equal to 0. So, Vx is equal to 80 plus 10x. So, Vx is equal to 80 minus 10x minus 10x. Okay. Now, this is the shear force, and if I take summation of mx is equal to 0, this gives mx, which is clockwise, plus again this is clockwise, 10 into 8 minus x is the total length, and this is by 2 is equal to 0, and this gives me mx is equal to minus 5 8 minus x whole square. You see, so this is the distribution of shear force and distribution of moment in this part. Okay. Now let's see quickly some observation whether this distribution is consistent with the problem. You see, in this case x varies from 6 to 8 meter, right? Now if I substitute x is equal to 8, which is at the free end, your shear force and bending moment both should be 0. Substitute x is equal to 8 here, this is 0, substitute x is equal to here, bending moment is equal to 0. So this is consistent with the problem, right? Now another observation, shear force is linear and bending moment is quadratic, bending moment is one order higher. In the previous case, in the previous part, between B to C, if you remember, this was the variation of bending moment, a variation of shear force and variation of bending moment. So variation of shear force is linear and the variation of bending moment is quadratic, one order higher. Now if I draw the bending moment and shear force diagram for the same beam, it will be like this. This is the problem. A, C, B, first draw the shear force diagram. Now between A to C, shear force distribution was this, and between C to D, shear force distribution was this. Okay. Now your bending moment and shear force diagram will be you can verify this. This is linear, this value is 35 at x is equal to 0. Show you, this is x is equal to 0, it is 35, and then it varies linearly, and x is equal to 6, it becomes minus 15. So x is equal to 6, it becomes minus 15, and between that it is linear. So it is 15. This value is 15. Now let's see the shear force diagram for this. For this part, shear force distribution is this, where x changes from C to D. Substitute x is equal to location at C means 6, it becomes 80 minus 60, 20, and this is positive. So this is 20. So and then again it decreases linearly. So this decreases linearly. So this is your bending moment, this is your shear force diagram, and this value is 20. This value is 20. Okay. Now if you remember, this value is 20. This value is 25. Okay. Now this is the shear force diagram. Let's draw the bending moment diagram. Once again, now your bending moment distribution was this, for bending moment distribution was this for this part. X is equal to 0, bending moment x 35 minus 35. Okay, not this part. Where is that? your bending moment was bending moment. If you draw this bending moment diagram, your bending moment diagram will be something like this. Okay, it will be this at B, it is hinged, so it should be 0 here, and then it is like this and this. Your bending moment diagram will be 0. Okay, and these values will be 50, then 20, and you can determine again what is the maximum bending moment by dm dx is equal to 0, and get the value of x where your bending moment is maximum. Okay, so this is how you can draw the bending moment and shear force diagram. Now things will be more clear when you do more exercises. If you take any structural analysis book, there are many solved examples given, many exercise problems are given. I suggest you to go to those problems and attempt them. And another thing, by the end of this course, you see, for instance, if I take a cantilever beam like this, okay, now apply a load here, then this will deflect like this. And in order to say that this will deflect like this, we don't need any structural analysis course. Just by intuition, we can say that yes, if the load is applied downward, the deflection will be like this. So this we can say just by intuition, right? Structural analysis course is required to determine the value of deflection, determine the value of internal forces. Now, by quoting this example, what point I want to make is this: by the end of this course, you should be able to, if you solve more problems, you should be able to draw bending moment and shear force diagram based on your intuition, just by looking at the problem. Okay, and you should reach that level. Now, what would be the values of bending moment and shear force? For this, you need equilibrium equation and solution of linear system. But just to draw a typical bending moment diagram and shear force diagram for a given structure, you should be able to do that from your engineering sense, and that sense you need to develop. And for that, you need to solve several examples. Because of the time restriction, we could do few problems in the class, but I suggest you go through the problems given in the books. Okay, thank you. See you next week.